Now, in class, we're going to apply the integral test in many situations to determine the convergence or divergence of a number of series. But one thing that we can do is actually use this test to provide, to determine the convergence of a whole type of series. Okay, so first of all, let me tell you what series it is. If we're going to look at series of the form sum from 1 to infinity of 1 over n to the power p. Okay, so p is going to be some fixed number. A series that can be written like this is called a p-series, and it's just tradition. I mean, there's nothing special about the number p, except for one little thing that I'm going to show you in a second. But traditionally, they're called p-series. Well, it turns out that a p-series is convergent if and only if p is greater than 1. So even though this criterion does not tell us what the series converges to, and in fact for many of these series people are still trying to figure out what they converge to, but at least we know what if and when they converge. So how can I make such a bold statement? Well, all I have to do is prove it by using the integral test. Remember, all I have to do is show that the same thing happens to the integral that has that function as integrand. So let's see what happens. So what we're saying is that the sum from 1 to infinity of 1 over n to the p is going to have the same destiny as the integral from 1 to infinity of 1 over x to the p. But this one is an integral that we know very well how to integrate, and we know that there are two cases to consider. There's the case where p is not equal to 1, where we can use the power rule, and there's the case where p is equal to 1, where we have to integrate as a logarithm. Alright, so let's see what happens when p is not equal to 1. Well, it's a simple integration, as I said, just power rule, and using the definition of an improper integral that turns out to be the limit as k goes to infinity of 1 minus p over x to the power p minus 1 between k and 1. And once again, we have to distinguish two cases here, depending on whether p is greater than 1 or less than 1. If p is greater than 1, then we have a positive power in the denominator of the fraction inside. So as k goes to infinity is being raised to a positive power in the denominator, and that means that the fraction is going to go to 0, and therefore the integral is going to be convergent. Okay, in fact, it's going to be convergent to p minus 1. On the other hand, if p is less than 1, then we have a negative power in the denominator. A negative power in the denominator can be moved to a positive power in the numerator, but now as x or k goes to infinity, that number will become bigger and bigger, and therefore it will diverge to infinity. Alright, what about if p is equal to 1? That's the last remaining case. Well, in that case, the antiderivative is the ln x, which of course will go to infinity as k goes to infinity, and there again we have divergence. So we now know that these p-series will only converge if p is greater than 1, and they will converge in that case. One little word of warning. When students, for many students, first working with p-series and with other kinds of series and so on, sometimes there can be a little bit of confusion. In particular, one confusion that students often have is in being able to differentiate between a p-series that we've just seen, for which we've just seen the criteria for convergence, and a geometric series for which we know absolutely everything, right? So how do we differentiate between a p-series and a geometric series? It's not a difficult task, but you need to be focused and make sure that you do it correctly. The way to do it is you look at where the n is in the series. Okay, so if I write it like this, now this is exactly what we were saying a minute ago, and so, or in the last short video, and this is what we call a p-series. Well, where is n? N is going to be in the base of that power. Okay, so that's sort of looking at polynomials. That's another the reason I was alluding to earlier when I said, well, there is a little bit of a reason for that p. So what we're talking about is here the variable index n works as the base for a polynomial. On the other hand, if we look at a series which is written like this, Then we know that this is a geometric series, right? Well, okay, it's not the formula that you have seen before. You may want to write it like this, right? And yes, of course, there may be an a constant coefficient in front of everything, but that's basically the substance of a geometric series. And now, where is the where is the n in this case? It's in the exponent. So a geometric series is somewhat corresponding to an exponential kind of situation, while a p-series corresponds to a polynomial kind of situation. So try to practice with these two different kinds of series. Make sure first of all that you can identify which one is which, and then try to remember the criteria for their convergence. And remember, for a geometric series, if we have convergence, we know what it converges to. For a p-series, we only know if it converges, but generally we don't know what it converges to.